Welcome guys, welcome back to the second part of the OpenGL series that we have started. Yesterday we managed to draw a simple triangle on the screen. Today we are going to take it a bit further and understand new stuff, new things about OpenGL. As of right now, I switched to Linux because yesterday I was working on Windows, but I switched to Linux. So sorry for the audio and for the audio quality. So the code of yesterday can be found on GitHub. You just have to go on GitHub. You search for Colonel Miguel. Then you will arrive here. This is my profile. Then you can go on the repository space. You can go and just click on the first game in OpenGL. When you are here, you just have to click this copy, but for you I think it will be HTTPS, but for me it's SSL because it's my repository. And you just have to go in and clone it. You will do something like git clone and you will paste the URL, but me, I've already done it. So yesterday this is what we managed to do. So let me just clean and compile everything. This is what we managed to do yesterday to achieve. Yesterday we managed to achieve this simple yellow triangle on the screen and with a black background. But today the first thing that I want to change in this program is the background. Actually, I don't like the black background. I really don't. And second of all, maybe right now or at the end of this tutorial, we will think a way of how we can make this window responsive, because if I make it the full screen, you can see that the window position, pixel position on the screen doesn't adjust well. So we are going to work on this too. So this is where we left, and as of the code, this is the code. I just cloned it. I didn't do any modification to it. So the first thing we are going to change the background. Let me check it's recording. Yes, it's recording. We are going to change the background. So how can we do that? If I GL clear, okay, this is it. In the I think there's this function color, I think it's clear color, yeah, and it takes a red, green, blue, but it's from range 0.0 to 1.0. so we are going to do this and the alpha value is going to be this. So if I compile and execute it, you can see right now we have a white background with a yellow triangle. So this is the first thing. The second thing that I want is, look at this gel uint is actually unsigned integer. So let me just copy this and paste it here. And if you see well, here we create the vertex buffer object. Here we create a vertex array object buffer. So but you can see that is actually the same thing, you know. Here we generate the buffer, we bind the buffer, and we set the data, we send the data, the vertex data to the vertex buffer object. Here we generate, we bind, we enable the vertex attribute, we also bind the buffer. Maybe we can find a way to abstract this, but we will leave it to another point. So what I want us to do is, if we look at this one. This is what we did yesterday. Today we are going. This article is extended OpenGL initialization by Anton Gel whatever. The last modification was last year on the 28th of April. So following from the minimal step last time, it's useful to get some statistic on what the computer video driver can handle and specify some additional parameter for start SFML again. Check errors. We can set SFML in the same way as before, but add some extra check. This will tell us if we made mistakes such as calling function with the wrong parameter. Before initializing GLFW, we can set up an error callback which can use this data which we can use to spit out some error information, then exit the program. We create a little function. Yeah, this is done with GLFW, but we actually don't need it in SD, because in SDL I managed to come up with this little function here. With this little function. Yeah, this function. I managed to come with this function, and it kind of does what we want already. So setting minimal OpenGL version to use. So before creating a window with GLF, we can give it the numbers of int to set specific window and OpenGL setting. Our primary reason for doing this is to force OpenGL to use at least the minimum version of OpenGL that we are writing our code to support. For example, if we are using selection shaders, a feature from OpenGL 4, then we should probably stop the program from running if the driver can't support OpenGL 4. So this is how we set it up, and we've already done it in SDL. This is it here. We've already done it here. We set the major version, the minor version, the OpenGL context, and the profile. So we set it up. So if you have an idea of what version of OpenGL your driver support, you can change the forward. Actually, because this thing, the forward compatible profile disable all of the functionality in your chosen version from OpenGL that is marked as deprecated. You don't normally need this in, but it can be quite helpful for first timers to avoid accidentally using old parts of the API and forcing yourself to use the newer part. If you get the OpenGL 4.x quick reference card, then this means that all of the function in blue fonts are not available actually. So this forward compatible flag here. Okay. And by the way, on Linux I'm using Vim, so the core profile you can think of as the default. The alternative is compatible profile, which include features of OpenGL from older version. This might be handy if you were, for example, uploading an old OpenGL video game to a modern standard. Actually, you can also use the in-sync system to enable things like stereo cost peak rendering if supported by your hardware. See the GLF window guide for more information. We've already done it here. So multi-sample initializing MSAA, multi-sample initializing. While we're adding window ins, it's good to know that we can put anti-aliasing int here too. Even if our texture and colors are nicely filtered, the edges of our meshes and triangles are going to look jangled when see the triangle pixels along the diagonal edges of a triangle? Yes. OpenGL has a built-in smoothing algorithm that blurs over those parts called multi-sample anti-aliasing. Multi-sample anti-aliasing. MSAA. So multi-sample is a rendering technique using cryptography to smooth out the jangled pixelated edges of a 3D object. It works by calculating. So it means that like your triangle does things like this and it's going to put it straight. If I can draw again, and so it means that you normally draw a triangle like this. Sorry for the drawing, but if you don't apply the MSAA algorithm, what you are going to end up, so if we don't apply this, we are going to end up with something like this shape, this is what we call jangled, and by applying this we get to this one. So it's as if it comes here and it take this and it scratch it like this and it makes it to be smooth. So this is what it does. So we can come back. Yes, that this part is understood. The more color samples it takes around polygon edges, the more smoothed the result edges pixel will look. But it also gets more expensive. Set it to 16 before taking screen captures. You should see a difference in your triangle edges if you change this value. The default is 1 or off. So GLF window in GLF sample 8. So a zoomed in comparison of the two triangles. MS with 0 sample left and 60 sample right. So we can see it's much more smoother. This is an int. Multi-sampling initializing alias. So it's also in gels multi-sampling. Sample sampling. The numbers of samples used around the current pixel used for the multi-sampling, yes. Initializer and S here. GL. We are going to set it to 16, and if we were to run it, this is it. But if you were to reduce it, you can see, I don't know if you can see, but me, I can notice the little triangles, since there's no way to zoom in, zoom out from this program, but I can see it. So I can see we are going to leave it to 16. And actually, sorry guys, but I just want to copy AI hand digit. Okay, now I can is it. Window resolution and full screen. To change the resolution or start in full screen window, we can set the parameter of the GLF create function. To use full screen mode, we need to tell it which monitor to use, which is a new feature of GLF 3.1. We can get quite precise control over what renders on the different monitors, which you can read from the GLF online documentation. For now, we will use your primary monitor for full screen mode. You can ask GLF to give you a list of supported resolutions and video modes with GLF get window mode, which will be useful for supporting a range of machines. For full screen, we can just use the current desktop resolution and change our GLF up to this one. So set this to false to go back to window mode. Include full screen. The monitor, with the dimension if it's full screen. If it's full screen, I'm going to GLF primary monitor. If it's full screen. GLF video mode. The mode is get video. Hinting this property lets us use borderless full screen mode. In full screen mode. But in SDL I don't think this is blue bits. Hinting this property lets us use borderless full screen mode. Full screen, I think yes. Full screen desktop. Use of undefined full screen desktop. You see, this is full screen. Set window property, but what we can do since we want full screen, we just have to do bold full screen false. We will come here. Keyboard down. We check else if the event the key F for full screen. F for full screen. What I want for full screen is to full screen true. Full screen true. Handle drawing. No. Handle updates. If full screen is true, what we are going to do, SDL sets window full screen. Full screen application. Full screen. If I F you see, this is the mode. Escape. But there's this set window full screen mode. This application window, this display mode. This display mode, it says set the display mode to use when the window is visible and full screen. This only affects the display mode used when the window is full screen. To change the window size when the window is not full screen, use set window size. If the window is currently in the full screen state, this request is asynchronous on some Windows system. SDL display mode. The SDL display mode is also the structure that defines the display mode. The display this mode is associated with pixel format. I don't think, yeah, this is it. We toggle, and we accordingly put the width and the height. Yeah, I think this is it. A display mode. So, when we created window resizable, the pixel of the window. Now we can run in full screen. It's a little bit tricky to close the window through. You might want to close it immediately. Keyboard handling. This is the remember that the loop. Yeah. Let's disable full screen and give it a try. We will recall when we look to update our window width and window height. You'll notice that if you resize the window, the clear background color fills the window, but the triangle is drawn the same size. It's not scaling up to fill a large window. We need to update the OpenGL viewport size to the new window. Let's update it. Or we pull the event. Yes. DLF get window size. We get the window. Yeah. If we update, so the event, what we do is SDL get window size, the window width, the window height. But there's an error. Yes, a const value is going to change. So yes, and we take the new size and we will set the OpenGL viewport to scale with y 0.6.6.8. GL viewport, the x 0 0, yeah, and the width, window, and the height. Okay. Use program shader. Yes, and we compile. Yeah, and as we reside, the Windows is adjusting properly. You see, the window is adjusting properly. And we hit full screen. F for full screen. Okay. This is a really good progress. And we swap the buffer frame rate counters. If you want to know how fast the program is running, you can count how many times per second your while loop iterates. This is often referred to as frames per second, or FPS. You may find that the inverse millisecond per frame is more intuitive for measuring the performance of your program. So how many times per second your loop iterates? How many times per millisecond the inverse? We can work these numbers out and write the results into a title bar on the Windows. So first we get the current time, title, countdown, seconds. We get the current time, the current minus the previous, and the previous get the current. The FPS title is minus elapsed. Pretty FPS, but not everything, so it doesn't flick too much. This minus countdown. If it's less than 0 or greater, if elapsed is greater than 0 and less than 0, the FPS is divide 1 second. Create a string and put the FPS at the Windows title. F string title. Yeah, this is typical, but what? We can't just elapse time. The FPS. Print the FPS, but not every frame, so it doesn't flick it so much. Not every frame. The elapsed time. How fast? So the code handles events. GLF is actually small. It's very low. Anyway, floats. Previous second is exhibit time. SL get time get nanosecond. Current time. Get current time actually. ticks. Get the current value from the real time ticks. For a real world or get ticks for application within timing. Ticks delta time. For game ticks. Ticks. Old names. Yes. Title countdowns. Title countdowns. Then inside the loop. What we do is we get a current time. We get the current time. So what we do, now the elapsed time. Is the current minus the previous. Yeah, this is it. And the previous is equal to the current date. This is the current. To be the current. So you already have this. The only thing that remains is to draw the calculate the FPS. Actually, this is already the FPS, as I know. This is already the FPS, but we are going to draw it differently. Now in the updates, title countdown. I don't know what elapsed. I'm going to disable this just to see title count. If it's less than 0 and elapsed time is greater or equal, strictly greater, what do we do? Float FPS frame per second is 1 divided by the elapsed. This is what they're called millisecond per frame. Millisecond per frame. So what we do is create a string, put the FPS as a window title. This is simple. Here set the FPS as the window title. I don't want to set the FPS as a window title. No. I want to set the FPS as a window title 10. Printf is 10th. set window title. I really don't. I really don't want to set it up. So FPS, what I'm going to do is this. FPS. I'm going to draw it. I'm going to draw. But I don't have a renderer yet. How am I going to do it? How am I going to do it? Because I'm going to GL clear color. It's going to be 0. 0.4f, 0.3f, 0.2f, and 1.0f. How to draw a text on the screen in OpenGL using CL3? To draw a text on to draw a title on the screen using OpenGL, you must use SDLTTF to rasterize your text into a pixel surface, convert that surface into an OpenGL 2D texture, and then render it in onto the screen align quad to the rectangle using shaders or a photographic projection. OpenGL lacks built-in text render support, making this texture mapping method the standard approach. So I've worked with SDL before, and this is actually like you load some texture and restore into a surface. You get a surface, you put that surface into the renderer, but this is you rasterize the text into a surface, convert that into OpenGL 2D texture, and then render it onto the screen align quad. You must initialize both the base video system and a SDLTTF library. Load from your preferred size. Okay. So TTF initialize. This is it. TTF initialize. Sorry, CMake SDL. On my Linux machine, I have everything already installed. So TTF if I make this possible reason TTF, not TFF. TTF. Okay. And it still render properly. So what I have to do is I have to include SDL3 TTF, SDL3. Initialize the TTF what CF init. Initialize the boolean. Here we initialize it CF. Now is fs cache fc cache. How to list all the fonts available in actually guys, as I told you yesterday, this is how I use AI. Like, since Google has this quick AI response thing, so I make my researches as if I'm talking to a LLMs, and I get these quick responses, and I just continue my work, and it's when I'm offline or when I want to go on into the documentation, it's then that I go to the documentation. But as I'm working, I want to go quick, so I do this. So to list the fonts, reduce fc list. Okay, but I want to grab JetBrain. Wait, what? FC list. Jet now. Oh, FC list. Grab JetBrain. Ignore case. Okay, this is it. JetBrain mono. JetBrain's mono. JetBrain mono. From here into assets. Okay, then if I go into asset, if I go into asset, I have this font, so I can use it. So I have this font that I can use. So now back to back to I've worked with TF as a TTF, but yes, TF open fonts. I open the fonts because I want to render the FPS. Remember, so I've initialized the TTF library and then now I have to load the fonts. So TTF returns me a font the size open font. So what I do is TTF open fonts IO with properties. The file will be assets then 48 TTF returns the pointer to TTF destroy but before we quit, we have to wait TTF okay. Like the font is ready, but the text now you need to rasterize your text into a pixel surface, then convert that surface into an OpenGL 2D texture. So I have it to rasterize text. I convert the text to a surface, then I rasterize my text into a surface and I convert that surface to a OpenGL texture. I render that on the screen align quad. So what I do, render your title screen into a temporary CPU side software surface using TTF render text blend it. The color, why are we using the color here? I want a white, maybe. Anyway. Default to BGR or RGB formatting. Texture format, pixel format, RGB, XX. Text image 2D. Clean up CPU. It layers on top of the 3D alpha blending to ensure that the font edges are smooth. Then render a quad map. This is a lot of work. Wow. Actually, this is a hell lot of work. Like, look at this. Generated text surface. Surface, the FPS. So what we are going to do is int unsigned int unsigned int texture text height, create a text surface white color, SDL surface, text surface is TTF render text blend, TTF render text blended, the font, the text FPS, the length is the length texture surface. Get the text width is equal to the text surface width. The text height is equal to the text surface height. Generate OpenGL texture. OpenGL texture. GL gen texture one texture. GL gen texture. Texture. Glad. Text surface. Test texture. Bind texture. Glad bind texture. Glad bind texture. The target is gel texture. Array buffer. How to draw the on-screen OpenGL for that one. To draw, load, generate. Yes. Below the surface. Gen texture. I don't have this texture. I don't. GL texture. Modern. this later. This I actually don't want to load. I actually don't want to load this. Then in here, want to do SDL set window title of the application. Okay, GLF has this get function which gives every frame get the current time in second. Work out the time elapsed over the last frame by subtracting the current time from the previous time. Update the previous time to the current time so that this work on the next frame too. Next frame too. So I start here. This is good. Go there. I will not channel or subtract here. And this is simple. Actually, this is simple because the current time, let's say, is 50 seconds. Then I go to, let's turn it to red. Okay, let's turn it to, okay, let's turn it stroke to red. Okay, like, and now is in a background color. Now, like, this is the first one. This is the first one. This is the first time. By the time we get to this two, we are on 20 seconds. So the elapsed is equal to 20 s minus 50 s, which give us 5, which give us 5 seconds. Now we continue the next frame, the third frame. This is 20. We are not going to take from this previous, so that is why in this phase we set the previous seconds to equal to the current seconds, so that by the time we get here, we are going to do 20 seconds minus, not 20 seconds, but 30 seconds minus, which give us 10 seconds. And this is the elapsed, and this one plus this one here, is all is the elapsed. So this is why we do this line. So actually update the previous with the current time so that it works off. Work out the FPS, being careful, never divide by 0. Because updating the FPS text every frame will flick too much, reduce the updates to every 1 second. So by using a countdown time and going to every second, we reduce the updates. We reduce the updates by 1. So You may prefer to render this as a text on the screen, but we don't have the functionality to do that just yet. Actually, I wanted to do that, but it's a bit hard. So graphics programmers tend to measure time in milliseconds for performance reasons, so you might like to put the frame time in milliseconds next instead of the frame second. You might notice that. Okay, let's try to compile this. This is 60 frames per second. Post 50. Okay. You might notice that the frame rate is more or less exactly tied to a monitor refresh rate. What's happening here is that at the end of drawing loop, the get swap buffer call is waiting until your monitor is ready to refresh before swapping his back buffer. The hidden 3D image that we draw our triangle to with the visible front for buffer, which we see displayed on our window. This delay is to prevent any visible tearing of the display while the swap is happening. When you are analyzing the performance of a program or want to minimize latency at the cost of visual quality, then you can disable this by calling. When you want to minimize the latency at the cost of visual quality, you can disable this by calling GL swap interval, where the parameter is the numbers of screen updates to 1 for better performance, for better swapping buffer. The value of 0 means swap immediately. Lock to normal refresh rate of your monitor. Keep in mind that the frame rate is not an objective measure of how fast your code is. You can run but can't display faster than the refresh rate of the monitor. Rendering at 200 Hz is therefore not beneficial in the same way as it will be to, for example, game logic, which could make use of more time step per second, more detailed movement path stuff. Fast GPU clocks will give you huge numbers when drawing nothing. This doesn't really mean anything that you can compare against until you start drawing more involved scenes. Measuring frame rates and time is useful when optimizing some complex scene. If you are drawing at 30 FPS in a game with fast moving animation, it will be noticeable jerky look, but it might be okay in a minimal chess game. You can use the FPS counter to improve rendering techniques for to get it back to whatever your program reasonable level is. Remember that frame rate is dependent on your particular hardware configuration. You want to look at frame rate on your minimum spec machine. That said, on any machine it can give you a good idea of which techniques are relatively more GPU hungry than others. Anyways, let's continue. We're already about 187. It's easy to make mistakes writing shader program. It's a good first step to start collecting and printing error when they are not working. We skip this in Hello Triangle to keep the code shorter, but let's add it now. After each call of GL compile shader, we have two of them. After each call of GL compile shader, which we have two of them, we can check for compilation error using GL get shader IV. GL get shader IV. If we find there are errors, we can print the compilation log with GL get shader info log, which should tell us what the error is, what line number the shader what line number of the shader the error was on. This is our existing preferred shader compilation code. Okay. Compile shader. Okay, these two. We compile the vertex preferred shader after the compilation. Vertex shader program. Check for error. Get shader. Get shader IV. Why is it glad get shader IV? I don't understand. Why is it so now? Gel compile. Vertex shader program. Gel compile statue param. It's a glad. It refers back to glad. I don't like it. So we get after compiler, check for errors. Keep the code after call. Check for compilation errors. Error, capture the log and print it. Del true. The max. SM. Yeah, we don't want to allocate. It depends on the error. The error can be max length, actual length, slug. Get GL shader info log. Magley actual length. Error shader index did not compile. Okay. Get shaders. So, sorry for the call, guys. Max. Okay, what we can do here is if gen is SL ASP printf SDAS ASPS okay, how to write on write in a dynamic allocated string using as the offering. Okay, the most efficient way depends on whether you're formatting a string, argument, or continuous writing. If you want to consult a string dynamically variable, use split handle the text size calculation and memory allocation automatically. Dynamic string. So we call it slug. Slug. Now what we want to do is we have the length. as slug. Now what I want to do, we will not do it. So max length. Actual length. Slug. GL get shader info log. GL get shader info log. The shader vertex shader program. The buffer size, max length, the length, the actual length, the slug, fprintf. Now error, shader index you did not compile. Shader index you did not compile. Slug. Then at this point we have destroying application. The context, destroy the context in the window. Destroy ASL, destroy the context, user context, exit failure. Okay, then this is the same. Oops. This is the same thing. shader knife FPS. Get shader IE. Shader source we compile. Okay, after adding that check for both of try deliberately making it type in your shader code. By running R, you should get the much more useful compiler printout of your words and which line on the shader is on. Error can also occur in the linking stage. Yes. Shader index 2 not compiled file and declare. At the link it said this won't affect us until we have more complex shader, but we will see in the next article that it's possible to output a variable from your vertex shader to your fragment. It's possible to output a variable from your vertex shader to a fragment shader. If the output / input data type doesn't match, you will get a linker error that this check will catch. We can put this check in now too. It goes after our call to GL link program. After the linking stage, shader program. Our shader program. Get GL program IV. Get shader program GL link statue params link statue params. delete shader program. Yeah, shader program shader. Yeah, error could not be linked. Program shader. Error could not be linked. Will not be linked. Shader program GL index u shader program role. You can see that it will make sense here to write a couple of helper functions for loading and checking. My advice is to try to keep this very simple. We will just one or two small functions actually, because okay, after linking, when we call it clean all the resources we created in our hero plan, but what if we create a larger plan? I want to clean up. After linking the shader with here, you can actually delete both of the compile shader. The plan will still work. Call gel delete shader for a vertex shader and a fragment shader. Delete shader, delete shader, the shader, vertex shader program. After a vertex shader and fragment shader. After linking, yes, if you wish to delete a shader program, call delete program. You might want to do this if you wish to live edit. If you wish to delete a shader program, call. If if you wish to delete a shader program call. You might want to do this if you wish to live edit or recreate a shader internally while your program is running. Really handy while you're learning about shader later. Hot reloading shader. You can delete a vertex array object. Vertex array object will delete vertex arrays. The first parameter a similar style vertex array. The first parameter is for the value. And the first parameter of value 1 is because the function can also delete an array of VAOs. Notice that this doesn't delete the vertex buffer object VBO with the actual vertex value. Vertex buffer VBO. Delete vertex buffer. Delete buffer the count VBO. Delete vertex buffer. Array VAO buffer. We will look at shader in more detail in next article, so our extra error logs will come in handy. Really handy. We've started to get some insight into how OpenGL works and how to debug some issue. For a real insightful look at what the state machine is doing, the RenderDog tool is a fantastic debugging companion to application development. It might not be clear what it's doing just yet, but when we look at the different hardware and shader pipeline stages, it will become very useful. Troubleshoot. So RenderDog is a free MIT licensed standalone graphic debugger. Allows quick and easy single pane capture and detailed inspection of any application. Volta, Helix, Linux. Okay guys, so the article is finished. So we still end up with a triangle, but you see, we've break the program. Maybe I think it's because I think it's because of here. Actually because we delayed the buffer VBO here. since we deleted it here, it looks like we deleted here, but okay, so we have like the triangle is responsive. Look at the FPSs. We can go full screen mode. It's okay, like just, but guys, look at this. This is a lot of like this part here. This code. I want to abstract this. Into a function. I want to abstract this error shader params -1. Xlog. I take the shader and sign in shader. But don't want to delete it here. Don't want to delete it here. Yes, I want to delete it here. So this is it. I actually don't want it. Yeah, I actually don't want it. And we come here, we look at this. Destroy the current context. And we destroy the window. Yeah, we don't destroy it there. But shader. What? VPS. Okay, so it this is it. We do the same thing. Share FPS. Same goddamn thing. Shader. Simple. Okay. Now what we want to do is the creation of the shader, of those shader, of these shaders. to do. The vertex buffer. Create and it gives us back a buffer. Vertex buffer shader, vertex shader, v vertex shader, fragment shader, shader type, shader type. The different kind of shader. Vertex shader, fragment shader, okay. Then let's replay it again. Okay. Then we are going to okay guys, I think we will stop for this for today, like this for today, and tomorrow we will continue on improving this. So pick up guys and see you later. Let's just go again and build it. Okay, see you guys.